All right, we are starting EQ 24. This is called VSEPR theory. I know it doesn't spell Vesper, but that's how we say it. And I can make the very safe guess that this is going to be most of your least favorite topics of the third 9 weeks. It's just not that interesting. It doesn't really carry over much into what we talk about later. But it's just something you kind of have to learn. So I apologize in advance for the boredom that you're about to go through. But tomorrow you at least get to play with these little, well, maybe, is it tomorrow? I don't know. I don't remember anymore. But you get to play with these little ball and stick models and build super fun things. So this one you can spin like a top. It's fun. All right. So that's kind of your payoff, as you get to play with those after you learn all of this stuff about VSEPR. So VSEPR stands for valence shell electron pair repulsion. And your EQ is, what do we use VSEPR theory for? Okay, so you should have already copied that down. Hopefully you did. If not, it should be on the board, or you do now, or go online. All right, what do we use the VSEPR theory for? So this is just a little bit of information before you start filling out your chart. So again, what it stands for, which you should write down, okay, it stands for valence shell electron pair repulsion. And I'm actually going to have you guys pause this for a few minutes so you can copy these 5 bullet points down, and then I'll explain them. So pause it now. Okay. So think about what this is saying. Valence shell electron, right? So we just know those are valence electrons, right? Outer shell electrons. Pair repulsion. So we know that all around the nucleus we have electrons, and we know some of them are paired up, right, in lone pairs, and then some of them are by themselves, and those are the ones that will form bonds eventually. But what we know about all electrons, regardless of whether they're in pairs or they're bonded, is that they're going to repel each other, right? They're all negative, therefore they don't want to be near each other. So what VSEPR does is it predicts the shape of atoms based on the electron's ability to repel one another. Okay, that's all it is. That's all it means. It's not super complicated. It's just a lot to remember. It's a lot to memorize, and it's not very interesting, which makes it harder to memorize. So VSEPR theory predicts the shape of compounds. That's the point of VSEPR. And then, as I just said, electrons around the central atom repel as much as possible. Okay, so when we start building these compounds, kind of like this one, we're going to talk about the central atom. So that's this one in this case. And then talk about kind of the angles that form based on how far away, sorry, I'm really bad at this, the angles that form between these atoms that are bonded to the center atom based on the electrons in each one of these bonds repelling each other. Okay? A couple things to remember. Lone pairs will take up the most space. So when you have a center, this is a good example, when you have a center atom that's got lone pairs around it, those lone pairs are able to spread out more because they're not locked into a bond, so they can take up more space, forcing the bonds to kind of, bend together a little bit. Okay? And then to decide shape, you only look at what's connected to the center. Okay? So again, I have a billion of these, so you just want to look at the center atom, not all of these ones. The center determines the shape. All right, so you guys, I believe, copied down this chart, which I'll zoom out a little. So I have a slide for each one of these, but then I can go ahead and fill this in with you just so you have it, you have an example as well. All right, hold on, I gotta get a little bit more organized. I don't want to write on my table. So this is what I should do. Instead of stacking them, I need to have them off to the side. Okay, so first one is called linear number 1. And linear number 1 is going to go in this first shape name box. Okay, they're going to be separate, linear number 1 and linear number 2. All right, so linear 1. I'm gonna write with a fine tip marker. Okay, so if something's linear, hopefully you know that means it's a straight line, right? If something's in a linear form, it's a straight line. So the first type of linear atom we have, it's just one atom attached to the center atom, or an easier way of saying that would be just in this box right here. So number of atoms bonded to the center, you just put 1, okay? Number of lone pairs around the center, you're going to put varies. And in all honesty, I'm probably just not going to ask you much about the lone pairs in a linear structure because they can be so different, okay? So don't necessarily worry about what, that means or anything like that. So this is the simplest we get. And this is an example. Okay, this is, notice, doesn't really matter which one you count as the center. All right, it's just one atom attached to another atom, and they're sharing one pair of electrons. All right, so it looks just like that. So rough sketch. These are going to get a little tricky as we go. Just realize I understand you all can't be artists like I am because you all know my artistic abilities blow your mind every time I draw on the board. So stick with me. We'll do our best to draw these. Okay, so some of you I'm sure will be fantastic at drawing these. I am not, so draw something like that so you know what it looks like. All right, and then some examples. I'll put a couple. I'll put more than one for the example box. A couple of things. All of our diatomic molecules will have this shape. All right, so actually, let's go ahead. I've never done this before, but I'm going to have you write this in there. I'm going to have you write in Brinkelhoff. All right, all of the elements in Brinkelhoff represent this shape. All right, so it would be Br2, I2, N2, Cl2, H2, O2, and F2. All of them would have this shape. If it's a double bond, so particularly in this case, oxygen would be the only one that would have to form a double bond. It would look like that. Okay, but notice it's still linear. It's just got 2 pairs of electrons being shared instead of just the 1 pair of electrons being shared. All right, so notice no different shape. It's still straight across. And straight across, just this one's with a double bond, that one's with a single bond. But every element in Brinkelhoff will form this shape. Okay. Next one. Actually, I don't even know if I'm going to go through the PowerPoint. I think I'm just going to fill out the chart. So let's move back over here. The next one is called linear 2. Okay, because we actually have 2 options when it comes to linear. And this is the other option. All right, it's got extra holes in it. We're going to ignore those for now, but this would be your other linear option. All right, so notice this is our center. How many atoms are bonded to the center? Hopefully you're counting 1, 2. All right. And then the number of lone pairs. So realize, can these 2 atoms get any further apart? Would they be able to, around the center atom, could they spread out any further? Your answer really should be no, right? At this point, they are 180 degrees apart. They cannot get any further, which means it's telling you there's nothing else going on around the center atom. If these can repel as much as possible, there's nothing else around the center atom. So the number of lone pairs around the center is 0. All right, and this is what the slide would have looked like. Okay, so again, something like that. 2 atoms attached to the center, 0 lone pairs. And this PowerPoint is on Edline if you want to go and click through it. On Edline, as long as it loads okay, these actually rotate. So they give you a 3-dimensional look. Obviously, I'm not Harry Potter. I can't make this rotate on paper, so that's why I built them, so you can at least sort of see the 3-dimensional look to them. All right, so a sketch. So now you just want to put I'm just going to bubble it in so you can tell it's kind of different. So you've got a center atom, right? And then you've got two atoms attached to each side, but no lone pairs. Don't draw anything else around it. Okay? Another example of this would be one like this. Okay? Notice the only difference, single bonds, double bonds. Okay, you see the two bonds, one there and one there, or one there and one there. That's what a double bond, single bond. But notice they're the same shape. They are directly straight across. All right, so some examples. We could say something like CO2, right? Carbon dioxide, where this is the carbon, and these are the two oxygens. And I can't represent triple bonds, unfortunately, so if we were to look at this and not count these as single bonds, we could say something like, I draw a line to divide those. You'd have H, 2 carbons triple bonded, and then a hydrogen. All right, and I'll zoom in on that so you can see what I just wrote. All right, so it'd be more like, that would also be linear. I know that there's more than one center, but still, if you look at this carbon as the center, it's got 2 bonded to it, and this carbon as the center, it's got 2 bonded to it. To build that, I could probably do that real quick, just so you would have an idea. Again, it's not perfect because with these building kits, you can't make triple bonds, unfortunately. Not a thing. But I can do my best to throw in another piece. Sorry, you guys can't see at all what I'm doing right now. But if I were to break this apart, just add another silver piece in, zoom out a little. Alright, so it would be something like that. Again, this would be a triple bond and these would be single bonds, but overall you can still see completely linear shape, right? Straight up and down, straight across. Nothing has an angle other than 180 degrees. Okay? Next shape is this the order I want to go in? No, we're going to do this one next. No, let's go ahead. Next one is the bent shape. All right, sorry, bent shape. And an example, perfect example is water, or a molecule or a compound that looks like that. Okay, so notice, are these 180 degrees apart? This angle, this atom compared to this atom? No, of course they're not, right? If you see them, they are not. I could push it down to try to make it like that, but it looks like it's bent, right? Like it's angular, it's got an angle to it. So what we know about the center atom, okay, first off, how many atoms are bonded to the center? We know the red is the center and the 2 white ones are bonded to it, so there's 2. All right, so notice the difference, 2 here. And then the number of lone pairs around the center. In order for the octet rule to be met, so we know we've got 2 electrons here, 2 electrons here. In order for the octet rule to be met, that means there still needs to be 4 more electrons, right? So it's 2, 4, 6, and 8, which means that there are also 2 lone pairs around the center atom. So as we said on the first slide, lone pairs take up more space. Okay, they're able to spread out up here a lot more. And if you, let's see, if I draw this down here on the paper, I can draw in, I can kind of draw the lone pairs in on the paper. All right, so that's what that would look like. So these lone pairs are actually able to take up much more space than the bonds are because those electrons are not locked into bonds. They're not being shared between 2 different clouds. So they can spread out more. So those lone pairs are actually what force these 2 bonds to bend down. All right, so that's what gives it this bent shape. So a sketch, again, it's going to be a little rough. So we've got a center. And then instead of drawing them straight out, we're going to draw them at a bent angle down instead. All right, so something like that. And again, the best example that could be given is H2O, water. All right, most prime example for the bent shape is water. Good. All right, so we're just going to try to go directly up in order. So if you look at the way our numbers are going, number of atoms bonded to the center, we've got 1, we've got 2 2s. So our only next option is 3. So this next one is called trigonal or trigonal, however you want to say it, planar, P-L-A-N-A-R, trigonal planar. All right, so as soon as you see trigonal, okay, trigonal, it sounds like triangle. How many sides does a triangle have? Hopefully you guys are saying 3. So it actually is telling us by having the name trigonal planar, it's got 3 elements or 3 atoms bonded to its center, and it looks something like this. All right, notice it's completely flat with the paper. It looks like the flux capacitor. If you don't understand that, then I don't have anything else to say to you. But trigonal planar, so it's flat with the paper. It's all on the same plane. That's why it's called trigonal planar. Notice, could these be any more spread out than they are right now? Hopefully you're saying no. All of these are all 128 degrees apart. These can't spread out any more than they are right now, which is telling us there is nothing else around the center. So it is 0 lone pairs around the center. Okay. A rough sketch. This is where they start to get a little more difficult to draw, but we're going to draw that center filled in. And just draw it directly like the way it is, just like that. Okay, so you're going to draw 1 off the top, and then 1 off each side. All right, again, trying to draw them as evenly as possible around the center. Some examples of this, we've got any time that boron is in the center, right? We talked about boron being an exception, that boron can only form 3 bonds and it's stable at 6. So anytime boron's in the center, it would have this shape. So we're going to put maybe something like BH3 would work. Also, let me see if I can switch this around real quick. You're going to find these are not easy to take apart when you start messing with them later on in the week. We could have something like this as well. So notice 2 single bonds and then 1 double bond would still give us the trigonal planar shape. All right, so you would have something like carbon, oxygen, and then maybe 2 hydrogens, something like that. So I'm going to put that as an example too. We'd have CH2O. Okay, a carbon, an oxygen, double bonded, and then 2 hydrogens single bonded to the carbon. All right, again, still trigonal planar, it's just not all single bonds, there's a double bond involved as well now. All right, moving on. So we had 2 options with 2, and it's the same with 3. Our other with 3 atoms bonded to the center is called trigonal. Okay, so the word is the same, but the second word is pyramidal, which hopefully telling these apart should be pretty easy, because planar we know means flat, right, all on the same plane. Pyramidal looks something like this. Notice, look how it's not completely flat on the paper. It looks like a tripod. All right, and I know that's kind of hard to see on camera, but notice these are not all on the same plane. Okay, this actually stands up on its 3. You can push it down to make it planar, but it pops right back up. And you're going to build this later, so you'll see. Okay, I can actually can spin it on the middle, which shows you that they're not all on the same plane. Okay? So 3 atoms bonded to the center, and again, to meet the octet rule, if we've got 3 atoms bonded, so we've got 2, 4, 6 electrons, then how many lone pairs are there room for around the center? It's got 2 electrons, 4 electrons, 6 electrons in bonds. That leaves 2 electrons left to meet the octet rule, or 1 lone pair. So again, notice all of these, just like the bent one, all of these are being pushed together because the lone pair at the top is spreading out and taking up more space. So it forces all of those bonds to kind of bend together and form that pyramid shape. Good luck with the sketch. I'm not even sure how to draw this. Well, let's give it a whirl. So let's draw our center. Maybe, oh goodness. I can't remember how I used to draw this. Draw maybe one coming directly out of the center, and then 2 coming out of the sides, kind of like that. It's not perfect by any means, but it at least adds a little dimension to it. Sorry, that got blurry. There you go. And again, these don't have to be, this is for your studying purposes only, so completely up to you guys how you want to draw them. Examples of trigonal pyramidal. I just dropped all of my papers on the floor. I'm gonna have to get those in a second. The easiest one is NH3, right? We know nitrogen, right? If we were gonna look at nitrogen's dot diagram, which I'll just draw off to the side over here, we know nitrogen's got 5 valence electrons, right? So it has room to form those 3 bonds, and then has that 1 lone pair at the top. Anything with phosphorus in the center as well, at least not breaking rules, would form this shape as well. So far, hopefully so good. All right, moving on to the next shape. If you guys bear with me for a second, I have to get up and get my papers. My feet. Not that you guys care, but today is actually, let's see what happened in school today. You took your 3rd and 4th period exams. So obviously, Jameson's still with me right now. My feet have never been this swollen in my entire life. They hurt. Just thought I'd share that with you. Okay, let's keep going. So next one, obviously you know after the 2 3s, our next option is 4. All right, so that's how many atoms are going to be bonded to our center, and that is called the tetrahedral shape. All right, I'm going to zoom out so that focuses a little. Tetrahedral, we already know tetra means 4, so this one's pretty easy to remember. Okay, tetrahedral, 4 atoms bonded to the center. All right, if there are 4 atoms bonded to the center, it's going to look something like this, right? And this one can be somewhat confusing. So I have another example to show you. A lot of times people picture this when there's 4 atoms bonded to the center, right? With all of these being 90-degree angles. But the problem with this is not all of the space around the center is being utilized. Remember, these are going to spread out as much as they can. They're not all going to stay on one plane if they don't have to, because there's more room. Notice none of this space over here is being used, and none of the space on this side is being used. If we do this, then all of the space around this center atom is being used. So these are a little bit bigger than 90 degrees. Okay, these bonds here, slightly bigger than 90 degrees. So this just utilizes the space more. But notice, if there are 4 atoms bonded to the center, are there any lone pairs? Your answer should be no, absolutely not. There's no more room for any electrons, at least if none of the rules are being broken, which in this case they're not. So 4 bonded to the center, no lone pairs. to draw this, let's give this one a shot. We'll draw our center. And then let's see, we can draw one sticking right up out of the center. Okay, so this is actually gonna, like, notice how this one looked like a tripod? This one's gonna look like a tripod, but with a camera sticking out of the top of it. All right, so then we can draw one off to the side here, one off to the side here, and then one kind of coming directly out of the middle. And again, you guys are probably, some of you are gonna have better artistic skills than I am at drawing 3D shapes like this, but that's the best I can come up with. It's not too bad. Which elements are the ones that we know can form, really, what's the main element that we know that can form 4 bonds? From 4A, right? Group 4A means they have 4 bonding electrons, so 4 possible bonds. We know obviously the most popular one would be carbon, right? So it can have CH4, right? Something like that. And then obviously we could have silicon in the middle as well. Those are really the main 2 that we talked about. All right. So those would be your options for the center of a tetrahedral. Would be carbon with whatever attached to it that could form 1 bond apiece. So it could, that could also say CF4, right? Or CCl4. As long as they can form 1 bond, they can go there. All right, we have 2 left. We're getting there. I told you this is not fun, but we're powering through. Next one. So unfortunately we have to use that word trigonal again, which is where studying is going to be very useful because you now have 3 that begin with trigonal and you're going to have to remember the difference between all of them. All right, so this one is called trigonal bipyramidal. Right, so we have trigonal pyramidal, now we have trigonal bipyramidal. And this one can be a little bit confusing, I'm not going to lie to you. This one can cause some problems. So this is where rules start to get broken for these last 2. The number of atoms bonded to the center in this one is actually 5. And it's going to look something like this. Right, notice 1, 2, 3, 4, 5. If it already is breaking the rule having more atoms bonded to it, there certainly isn't room for any lone pairs. So this is 0. Okay. To draw this, stick with me, okay? So what I want you to notice about this is actually linear, okay, right? You can see right here, these are linear with each other, combined with trigonal planar. Right, it's just those 2 shapes put together. Linear, right here, right, going straight across this way, and then trigonal planar with these 3 coming out this way. So a way that might help you remember that this one has 5 is it's trigonal, right, trigonal bipyramidal. If you put tri and bi together, it makes 5. So that might be an easy way for you to remember 5. As far as drawing this, let's give this a shot. So I got my dot in the center. So we're going to draw 1 coming out of each side, all right, to get that linear view. And we're going to draw 1 coming out of the top, and then 2 kind of coming out of the bottom like that. All right, not bad, not bad. It's not perfect by any means, but it's similar. And when you guys build this one tomorrow, I think when you see this, when you actually get to build it, you're going to understand the shape a little bit better. All right, who is the one element we know that can do this, that can break the rule and form 5 bonds? Hopefully you're all remembering from when we talked about Lewis structures that phosphorus breaks this rule, right? So this could be something like PF5, right? Phosphorus in the center and then 5 fluorines bonded around it. Right, but this center must be phosphorus. Okay, phosphorus is the only one that can do that. All right, so if you want to make a note somewhere, that this must be phosphorus, then go ahead and do so. Our last shape is called, and this is going to take some explaining, so I apologize in advance, is called octahedral. Octahedral. And as I said, I apologize because this is where it gets weird. We know octa means 8, right? But in reality, this has 6 atoms bonded to its center. And I'm going to explain why that's what happens. I understand it's frustrating, but when you build this tomorrow, you'll hopefully be able to see it, is that when we have an octahedral shape, which is like this right here, notice 6 things bonded to the center, it actually makes an 8-sided figure. All right, it's got, think of as like 2 square pyramids stacked on top of one another. So it would have 1, 2, 3, 4. I know this is so difficult to see on the video. When you build this tomorrow, though, you'll see it makes an 8-sided figure, which is why we call it octahedral. So I apologize, but fun fact, when you build it, you can spin it like a top, and it's super fun to play with, and you guys can do that. I'm giving you permission, right? So that'll make up for the fact that it's a little bit confusing. So 6 atoms bonded to the center. Obviously, it's already breaking the rule with 6 bonded to the center, so no room for any lone pairs. To draw this, good luck. I think I draw a center one. I draw one coming like directly out of the center to give it at least sort of a 3-dimensional look. And then just draw 5 more around it and hope for the best. So there's 4, 5, 6. I don't know. I mean, it's not great, but at least it'll help you remember that it's got 6 things bonded to the center. I'm sure one of you can come up with a much better drawing of that than I could. Looks like a spider, but not a spider because it doesn't have 8 legs. It only got 6 legs, so it'd have to be an insect. And then who's the one element that we know breaks this rule and can form 6 bonds? Hopefully you are thinking sulfur, right? So that would be something like SF6, right? SF6. Okay, so you've got your whole chart filled out. At this point, we can go ahead and look back at some of these shapes to compare them if you want to. So remember, we had linear 1, where it's just 2 bonded to one another, either with a double bond or a single bond, like that, right? I'm going to try to leave these all on here. I don't know if it'll fit. We've got bent. Where did my bent? There it is. Oh, I'm sorry. My fault. We've got linear 2, which we said looked something like this, right? 1 in the center, and then 2 coming out of the sides. Right? We had something like that, or I think I took the other one apart. Definitely similar to that. We've got bent, which would look like this. Right, so notice these have similar setups, right? 1 in the center and 2 out to the side, but this one is called bent for a reason. It's because it's got the lone pairs at the top. They're pushing those angles down. Right, I'm going to move these ones so I can do the next couple. We've got trigonal planar, which would be something like, this, right? Or like this. These are both considered trigonal planar, right? But they're on the same plane, right? Completely flat with the paper. Notice this one doesn't really spin like a top on the paper because the whole thing is down. So trigonal planar, and then we've got trigonal pyramidal. Notice you can see the shadow under it, which shows that there's space underneath those bonds. And this one, if you see, this is the one you can spin because those aren't on the bottom. Those aren't on the same plane. They're not flat. So that one spins better. Okay, so that takes care of trigonal planar and trigonal pyramidal. We've got tetrahedral, 4 bonded to the center. Our only option for this one, 4. We've got trigonal bipyramidal, so 5 bonded to the center. No lone pairs. This one, maybe it doesn't spin well, but remember this one is a combination of linear and trigonal planar. All right, tri bi, 2 and 3, 5 total. And then our last one, octahedral. Remember, 6 atoms bonded to the center. It makes an 8-sided figure, which is why we call it octahedral. This is the super fun one that you can spin. Again, you guys get to build all of these to, I think it's tomorrow. You do this over 2 days because you won't have time to get through all 8 stations. So you're going to do 4 stations one day and 4 stations the next day. If you end up getting through if you end up finishing your 4 stations early, there's a worksheet attached, so you can just work on the worksheet. Don't rotate early. Don't do more than 4 stations a day because you're going to be bored the second day and then you're going to cause problems. So do 4 stations. You see my hand? 4 stations. Looks like I'm missing a thumb. There it is. 4 stations, and then work on the worksheet the first day, and then do the second 4, only 4 stations, and then finish the worksheet on that day. So you really shouldn't have much to do in terms of homework or anything like that. All right. So you guys will get to build all of these now that I get to take them apart. You guys will have all of these to mess with over the next couple of days. Hopefully this wasn't too brutal. I told you it's not very fun, but oh, here you go. I'm so smart that I added this on there. Why it's called octahedral. Okay, this is what it would look like if you were to put sides on it. So notice it's an 8-sided, like a diamond kind of, an 8-sided figure. Okay, so that's why it looks like that. And then kind of like that. All right, just trying to help. I think that's all I have for you. Sorry, this was a shorter video than I thought it would be. So if you guys have time, you can just chill for a little bit. You have my permission to take a bit of a break. You have a test, I believe, next week. So make sure you are preparing for that. Remember, tests you take by yourself. You are not working with anybody on a test. That's all you. All right, so study. You're going to get a study guide for it, and it says on the do now, but I'm telling you in my own words right now that the study guides while I'm gone are mandatory. Okay, they're not extra credit, or I'm sorry, they're not optional like they are when I'm there. But it's kind of an oxymoron. They are mandatory extra credits. So you have to do them to get the grade for them, but you're also going to get 5 points extra credit added onto your test. Okay, it's just my way of forcing you to do a little extra work to study so that you do well on the test. Okay, I think that's all I have for you. Sorry the cat is not around today to entertain you with her disgusting tail, so she's not here. But you have this chart. The PowerPoint that looks like this is all an Edline, and these rotate if you play it as a PowerPoint, so that might help you a little bit. Miss you guys, and I will see you soon. Have a fantastic day.